There's a new high-stakes race heating up across the globe, and it's not for space or for microchips. Nope, this is a race to completely redefine nuclear energy as we know it. The prize? Well, it's dominance in a technology that could literally power our world for the next 100 years. We're diving into the world of small modular reactors, or SMRs. For decades, when you thought of nuclear power, you pictured these gigantic, unbelievably complex plants. But here's the big question on everyone's mind. Are these new, smaller, factory-built reactors really the next chapter in the story of nuclear energy? Is this the leap forward we've been waiting for? And wow, this slide just nails the difference. I mean, look at this. On the left, you've got the classic picture of nuclear power, sprawling, custom-built, taking forever to construct. And on the right, you see the vision for SMRs, compact, sleek, something that looks like it could be built on an assembly line. This isn't just a size difference, it's a whole new philosophy. So, what exactly is an SMR? Okay, the official definition says it's a nuclear reactor with a capacity of up to 300 megawatts electrical, which for context is enough to power a few 100,000 homes. But the real magic is in those other words, modular and factory fabrication. The whole idea is to build these things like you build cars, not like you build one-of-a-kind cathedrals. So while the hype? Well, the appeal of SMRs really boils down to three huge promises. First, building them in a factory means they should be faster to build, and the quality should be way more consistent. Second, they're scalable. You can add more units as you need more power, which really lowers that massive upfront financial risk. And third, a lot of these new designs come with enhanced safety systems that use natural forces like gravity to cool the reactor in an emergency, which is a huge deal. And that promise, well, that's what's kicked off this absolutely fierce global competition. Major world powers are betting billions of dollars that SMRs are the future. And believe me, nobody wants to get left behind on this one. And here's a quick look at the projected battlefield for 2040. Right now, it looks like Western designs are set to take the lion's share of the market. But you absolutely cannot count out China. They are a rising powerhouse here. And Russia is playing a very smart, very niche game to stay relevant. Okay, so how is everyone planning to win this thing? Because it's definitely not a one-size-fits-all game. Let's break down three very different strategies that the major players are using to try and corner this emerging SMR market. This table gives us a fantastic snapshot. You've got Russia, which is carving out a really unique niche with floating power plants. Then there's China, basically hedging its bets with two different technologies at once. And in the West, it's this diverse, super competitive marketplace with a bunch of different companies and designs all fighting for the top spot. So let's start with Russia. What they've done is pretty clever. They've taken all their experience with nuclear-powered icebreakers and used it to create the world's first floating nuclear power plant. The idea is to bring power to remote Arctic communities where building a regular plant just isn't feasible. It's a really smart solution for a very specific problem, and it basically gives them a captive market from day one. Now, China's strategy is fascinating. They're going after this with a two-pronged attack. On one hand, they have the HTRPM, which is a totally revolutionary, brand new kind of gas-cooled reactor. On the other hand, they have the ACP100, which is an evolution of proven existing technology. It's kind of like betting on a high-risk, high-reward startup and a safe blue-chip stock at the exact same time, just hoping one of them pays off big. And then we get to the West, where it's really a tale of two different approaches. In the US, it's a market-driven free-for-all. You have private companies like NuScale and GE Hitachi all competing with their own unique designs. But over in the UK and France, it's more of a national champion model, where the government gets behind one major player, like Rolls-Royce, to be the country's main contender on the world stage. Okay, but for all the slick designs and ambitious strategies, the story takes a really sharp turn when we start looking at the actual data from the first reactors that are up and running. This, my friends, is the billion-dollar reality check. This quote just says it all, doesn't it? Because while the idea of SMRs is incredibly powerful, the first attempts to actually put them into practice have been, well, let's just say they've been really, really difficult. And you can bet that potential investors and future customers are watching these early results like hawks. So let's just start with this number, 28.5%. That was the average operational load factor for Russia's floating SMRs back in 2022. What does that mean? It means they were only actually generating power less than a third of the time.
For technology that's supposed to provide constant, reliable energy, that is a really tough start and a huge red flag for anyone thinking of buying one.
And if you thought that was low, look at this. China's revolutionary, cutting-edge HTR-PM reactor. It operated at just a 10% load factor in 2022. This just goes to show you the massive technical hurdles you face with these first-of-a-kind technologies. The theory is one thing. Making it work in the real world is a whole other ballgame. And then there's the other massive hurdle, the cost. Just look at this chart. A standard natural gas plant costs about $1,200 per kilowatt to build. The most optimistic SMR projections are almost 3 times that much. And others, like NuScale's design, are projected to cost over 5 times as much. That is an enormous price gap to overcome, and it makes the sales pitch to your local utility company incredibly hard. So let's just boil it down to the crucial point here. The first SMRs to get out of the starting gate are struggling with 2 fundamental make-or-break problems. They aren't yet reliable, and they are incredibly expensive. To win this race, you absolutely have to solve both of those issues, period. Which brings us to our final question. With these huge challenges staring them in the face, what is it actually going to take for any of these designs to cross the finish line and become a real commercial success? Well, this timeline really puts things in perspective. We are still in the super early innings of this game. Yeah, Russia and China got the first units online, but the first Western reactors aren't even expected until the end of this decade, maybe 2028 at the earliest. And widespread, affordable deployment? That's still a big question mark, probably not until 2033 or later. So what are the keys to victory? It's not just about being first. To win, any of these designs has to pass 4 critical tests. First, they have to prove they work. The next projects have to perform way, way better. Second, they have to prove that building them in a factory actually brings the costs down. Third, they need a ton of financial backing. And finally, they have to get through a maze of regulatory approvals. It's tall order. So in the end, it all boils down to this, right? The global race to build a smaller, safer nuclear reactor is on. There's no doubt about that. But the real challenge, the one that's going to decide the entire future of nuclear power, is whether anyone can build one that is also affordable and, most importantly, reliable. That's the billion-dollar question.